Hey there, in this video, we're going to go over some properties of transforms. They're going to allow us to find Laplace transforms and inverse Laplace transforms of a wider array of functions. So first, we're going to look at what it means to translate along the S domain. A translation is where we're shifting a function, and it turns out if I take some function f of t and multiply it by e to the at, where a is some real number, then that's going to just take the function f of t, and it's going to translate or slide its Laplace transform by that same number of units of a. So if I have a Laplace of e to the at times f of t, then the result I would get would be f of s minus a instead of just f of s. And with the Laplace inverse, the same thing. If I'm taking the inverse of f of s minus a, then I'm just going to get the function f of t times that e to the at after I take the Laplace inverse of it. And this isn't necessary, but a helpful notation you might find is kind of an intermediate way of getting from the original function to its translation is you can say, well, the Laplace of e to the at times f of t is the Laplace of f of t, only where s is replaced with s minus a. So it's a kind of really just kind of swapping those out when you're doing one of these translations. So to better understand this, let's look at an example. Okay, so I want to find the Laplace transform of e to the 2t times cosine of 5t. So that e to the 2t is a big warning for me that I'm doing a translation along the S domain of the function cosine of 5t. So I want to start out with finding the Laplace of cosine of 5t, and then I'll translate it using the 2 from the e to the 2t. So the Laplace of cosine of 5t would be s over s squared plus that 5 squared, or 25. And so the multiplying cosine of 5t times e to the 2t just means that I'm replacing the s's with s minus 2. So my translated function is going to be f of s minus 2, which is going to be s minus 2 on the top. So I just replaced s with s minus 2. And then over s minus 2 squared plus the 25. And that's really all there is to it when we're doing these translations. It can be particularly helpful when you're going backwards. So if I had the one we ended up with here, I can look at that as a translation and find the Laplace inverse and get back to that e to the 2t times cosine 5t without too much difficulty. Oh, and I can simplify this by distributing out the s minus 2 squared. And then I get the completely simplified version. If I was doing the inverse and reversing this process, I would complete the square on that denominator since it's not a factorable trinomial there at the bottom. So I'd complete the square on the last 2 to get this back to that form of the s minus 2 squared plus 25. Okay, so some common translation formulas that we will often use when trying to solve a differential equation is when I'm multiplying e to the at times t to the n times cosine to the kt, or cosine of kt, and sine of kt. With each one of these, I'm just replacing the s's with s minus a. The other property we want to look at in this section is convolution of transforms. So convolution is kind of like a made up or fancy multiplication that we come up with. And it is kind of reminiscent of our Laplace transforms because we're applying an integral, but it is a little bit different from a Laplace transform. So I'm going to use this symbol. It's like an asterisk in place of the multiplication symbol. So f convoluted with g of t is equal to the integral from 0 to t of f of tau. I mean, if you really don't like the Greek letter tau here, which is kind of a curvy t, then you can use different letters, but just don't make sure it's a distinctive from the t, because the t and the tau are different variables here. So it's the integral from 0 to t of f of tau times g of t minus tau, and we're going to integrate this with respect to tau. Okay, so let's do an example with this before we see how this ties into what we're doing with Laplace transforms. So I want to find the convolution of e to the 2t convoluted with 3t squared. Now, just bring back that formula again. The convolution of f and g is going to be the integral from 0 to t of f of tau times g of t minus tau d tau. So my first function, e to the 2t, is going to be f, and 3t squared will be g. So setting up this definition for convolution, I get the integral from 0 to t of e to the 2 tau times 3 times t minus tau squared d tau. I'm going to use integration by parts. I'm going to pull the 3 out in front of the whole integral and just focus on the e to the 2 tau times the t minus tau squared. Since it's a product of functions, integration by parts is going to work really well here. And I'm going to use the tabular method just to make it a little more streamlined, since we would have to do integration by parts a couple of times. So e to the 2 tau is always going to be my last choice for u. So I'm going to make that dv, and the t minus tau squared will be u. Taking the derivative of t minus tau squared, I'm going to get negative 2 times t minus tau. Again, I'm just doing the power rule there and chain rule, taking the derivative with respect to tau. Taking the derivative of the negative 2 times t minus tau is going to give me a 2. And then the derivative of that will be 0. And so now I'm going to integrate the same number of times with the e to the 2 tau. That'll give me a 1/2 e to the 2 tau, then a 1/4 e to the 2 tau, and finally a 1/8 e to the 2 tau. And then for using the tabular method, you're not going to multiply down the 3 diagonals you get, alternating the sign plus and minus to go with the formula uv minus the integral of v du. Okay, so if I put all that together now, I'm going to end up with this integral here. I've got the 3 out front, and now I have 1/2 t minus tau squared e to the 2 tau plus 1/2 t minus tau e to the 2 tau plus 1/4 e to the 2 tau. So I'm just multiplying those diagonals and simplifying as I go. Next, I'm going to evaluate the limits of integration. So I'll plug in the upper limit t into this whole thing, and then subtract 0 plugged into this. And so that's going to look something like this. Again, I've got the 3 just multiplying by each set. So the first set of brackets is where t is plugged in, and I can see some things that are zeroing out where I end up with the t minus t. So really the last term, the 1/4 e to the 2t, is the only one that ends up being non-zero in the first set. And then in the second set, I got a lot of zeros that simplify, and I end up with 3/4 e to the 2t, and that came from the first set of brackets. And then minus 3/2 t squared, minus 3/2 t, minus 3/4. And that gives me my answer for that convolution. Okay, so how can we use convolution when we're doing Laplace transforms and inverse Laplace transforms? Well, the convolution theorem will help us out here. So let's say I'm taking the Laplace of f of t and g of t, and I get f of s and g of s out of those transforms, respectively. Well, it turns out that if I take the Laplace of the convolution of f and g, then I get the product of big F of s times g of s. This isn't where things are terribly helpful. What really gets helpful is when I reverse this, or take the inverse of this for the inverse Laplace. So this means that if I take or apply the inverse Laplace to a product of functions, I get the convolution of little f and g. So we can use these in problems where I have a product that I want to find the inverse transform of, and really all I need to do is find the inverse transform for each of those functions individually. So for big F and big G, find the inverse transforms. And then I do the convolution of those two resulting functions to find my inverse Laplace. So that can be really helpful in the process of solving a differential equation.